learners, welcome to the next session. In this session, we are going to discuss about quantum reinforcement learning. So the lecture outline is quantum reinforcement learning, QRL approaches and quantum native RL and QRL algorithms. A novel quantum reinforcement learning is based on quantum theory and reinforcement learning approach. So superposition principle is the backbone of this approach. State and action value is represented with the quantum state. Probability of action eigenvalue is denoted by probability amplitude, which is updated according to the rewards. This approach makes a good trade-off between exploration and exploitation using probability and can speed up the learning. The result of simulated experiment verified its effectiveness, and we can easily check with the other kind of data. So reinforcement learning uses a scalar value named reward to evaluate the input-output pairs and learns by interaction with environmental through trial and error methods. Here, in quantum information technology, information unit is represented with quantum state, and qubits is an arbitrary superposition state of two-state quantum system. Ket psi, which is equal to lambda ket 0 plus beta ket 1, where lambda and beta are complex coefficient and satisfy lambda square plus beta square, which is equal to 1 times of ket 0 and ket 1, correspond to logic state 0 and 1. Lambda squared and beta squared represent the occurrence of probability of ket 0 and ket 1 respectively when this qubit is measured. Quantum enhanced reinforcement learning, this algorithm speed up the classical RL process such as state exploration or policy optimization. And this is also used to enhance the computational heavy tasks such as optimization, function approximation or policy evaluation. So, but quantum algorithms speed up the specific subtasks also comparatively with classical algorithms. In quantum enhanced Q algorithm, when we are going to compare with the classical Q learning, agent update the table of the Q values for the state action pairs using the Bellman equation. Quantum computing can also to be used for faster functional approximation using quantum support vector machine for speed up the values functions updates in the Groover search. A quantum enhanced Q learning agent could use quantum circuits to store and update its Q table. That is also very important. Quantum native RL. This is fully quantum approach where both the agent and environment operate with the quantum framework. Here, agent processes the quantum states and takes action in quantum environment. Quantum native RL lies on the concept of quantum superposition and quantum entanglement and quantum measurement. So the example here is quantum policy gradient. Quantum agent use a quantum neural network to approximate the policy function. Instead of classical probability distribution, the policy is represented by a quantum state, allowing for quantum parallelism. Training also to be performed using with the help of quantum gradients, and such techniques are also to be there for parameter shift rule to update the policy. The key principle is state superposition and quantum parallelism. In QRL, the state in traditional RL is represented as eigenstate in QRL. The state set can also to be represented with the quantum superposition state, allowing multiple states to easily process simultaneously. This method easily achieve quantum parallelism, which significantly speed up the learning process. Next is quantum measurement probability amplitude. The probability of the eigenvector we can easily determine with the help of probability amplitude, which is updated according to the reward values. This approach balances the effective values between probability amplitude guides the selection of the action based on their potential rewards. So QRL algorithm involves several steps: initialization, action selection, reward and update. You know that initialization we are going to set the states. In action we are going to measure the quantum state where each eigenvalue is to be correlated with the probability of amplitude, and reward after the execution of the action the system receives the reward and the probability amplitude is updated using Grover's iteration, which amplifies the probability of good action. And this is the very simple representation of the approach. So first, initially we are going to update the packages, and with the action state and action set, function to select an action based on the probability amplitude, function to update the probability amplitude based on the reward, and ensure the non-negative values to be prevent the diversion, zero division, and we are going to just approach the QRL algorithm execution with the help of different kind of action values. So finally we will get a different kind of action and reward, and with the help of amplitude values. So this is the very good approach. We can easily go with QRL, and the next challenges is this is very much important, limited availability of large scale quantum hardware, noise and decoherence in current quantum state, complexity in designing hybrid quantum classical architecture. Quantum reinforcement learning represents a promising frontier in machine learning and quantum computing applications, and quantum hardware continues to evolve. The potential of QRL to revolutionary approaches of problem solving and industries also. Thank you, learners. With that idea, we will close QRL session. We will see in the next session.